matter and material. So today we'll be dealing more specifically with calculations. Just a small recap. Remember that we have a work function, right? And a work function, in simple terms, you can say for an electron to be released from the surface of a material, energy has to be added to the material. So now the added energy needs to overcome the forces that the ions of the material exert on the electron. Now this amount of energy is called the work function, right? And we also dealt, or we spoke about the photoelectrons, right? And we said that all the energy of the incident photon is absorbed in the process, right? Now we said the part of the photon's energy is used to release the electron. This is the work function, right? And the remainder of the energy is converted into the maximum kinetic energy that is released and ejected electron is called the photoelectron, right? So now we have the cutoff frequency and the cutoff wavelength. And light, we know it has the dual nature, which is the wave nature and the particle nature. So now when we're going to solve this, there are two ways of solving a problem. Okay, I wrote here by mistake, it's fine. So this is what we can do. The problem solving strategy. We have to have a strategy, right? So the first strategy is that find the energy, right? E equals to HF, or E equals to HCF. Now from there, determine the work function. Work function is equals to Planck's constant multiplied by the cutoff frequency. So now we can simply say work function is equals to HC amplitude. Right, something like that. Now that is how we can go about writing it. So this is where we're going to play or spend most of the time as we deal with calculations. For 2 minutes I want us to do this activity. Example 1, it has what, let me see, it has two whatnot. So for one, number A, they said, okay, firstly they said a photon of green light has the wavelength is 510 nanometers, 510 nanometers nm. This is basically 510 times 10 to the negative 9, right? So this is our A here. They're saying calculate the energy of the photon. Remember, energy is equals to what? HF, where this is equals to HCF, amplitude. So now this is 6.63 times 10 to the negative 34, right? Then this one here is 3 by 10 to the what? To the 8, to the exponent 8, divided by what? 510 multiplied by 10 to the negative 9, right? So that's basically that. So now from then, when we calculate the energy, let's see how much we get there. Okay, so now let me see. The answer is going to be what? 3.9 times 10 to the negative 19 times 10 to the negative 19, right, like that, to the negative 19, right? So now That's cool. That's very good. Now looking at this, um, let's see. We have number B. With B, they said what? Use the work function, right? We have work function that is being provided for us, right? I just did not post it for you guys. Post it sometime later. So they said to determine the material of the whatnot that is released from that. So now, okay, look. According to the table, the work function of the closest material, the work function of the closest material is what? 3.36 times 10 to the what? Negative 19, right? So now that is basically that. So if the work function, and the work function of this is cesium, which is Ce. So yeah, that's basically that. Now this is how you can answer this, because they said look at the table. The work function that is closest to is this, which means cesium is closest to the green light, the energy of the green light. So now let's go to C. They said to you, determine the maximum kinetic energy. Now E equals to half mv squared. This is max, right? So now we already know that. Now, but then in our term, we're going to use hf minus the work function. So now, what are we going to do? We're going to take, remember we have the work function here, which is this one, and we have the energy, which is this one. We're just going to replace them. So we have what? 3.9 times 10 to the what? To the negative 19. Yeah, it is what it is. To the negative 19, then subtracted by what? Subtracted by 3.36 times 10 to the negative 19. Now, okay, we're good. So now this is equal to what? 5,4 times 10 to the negative 20 joules. Now that is energy. That's how you can answer the questions. So let's go to another type of question. Example number 2. So we have this. They said the wavelength of the light is what? 272 nanometers, right? Nanometers. So this is the wavelength. Now it is radiated on a tungsten. Remember, a tungsten is a very tough metal. I don't think there's any metal that is close to a tungsten. So basically the answer here is either gonna be 0, it's gonna be low. So now I said is radiated on the surface of a tungsten. Photoelectric effect, electrons are ejected with 0 kinetic energy. That's what I meant, right? So the energy is approximately gonna be 0 because the kinetic energy is 0. So now, but then let's look at let's see. They're saying to us calculate, or if the light of frequency is 9 times 10 to the 14 hertz is radiated to the metal, will the photoelectrons be ejected? The answer will be obviously no, because we know that tungsten is a heavy metal. It requires more frequency. So but then let's calculate that and see, right? So remember, FO equals to C over amplitude. Remember this formula. FO equals to what? C, no, sorry, I did it the wrong way. It's what? Let me use the red pen. It's been a while since I've changed the thing, the colors, right? Let me change them a bit. C equals to FO amplitude O, right? This is the equation. So now we can use the blue one. We say equals to what? Let's see. Here you have what? You have the wavelength and whatnot. So this is 3 times 10 to the negative, to the 8th divided by, for the wavelength part, we have what? 272, right? Now listen, they said to us that the wavelength of this is 272, right? So now the wavelength corresponds to the Kratov frequency. If we go to the table, right? So from the table we have to subtract 272 by what? By 2, then multiply this by 10 to the what? To the negative 9. That's basically what we need to do. We need to subtract 2 from this. So we're going to have what? 3 by 10 to the 8th divided by what? 270 by 10 to the negative 9. So now when we solve this, what do we get there? We get 1.1 times 10 to the 15 hertz. That is the frequency. So now number B, they say to you calculate the maximum kinetic energy of that, right? So now remember that the work function is going to be equal to what? HFO. So we have FO, which is this, and we have H, we know that is Planck's constant. So we just say 6.63 times 10 to the negative 34. Negative 34 multiplied by 1.1 times 10 to the what? To the 15, right? Now when we deal with this, we'll get what? 7.73 times 10 to the negative 19. Now if that is the case, we want the maximum kinetic energy, so we're going to say what? Remember, E equals to half mv squared max, right? This is E max, EK max. So this is equals to HF, okay, is equals to HF, okay, now minus what? Work function. So our HF in this case is going to be what? Is going to be HF, right? So we're going to have let's see, 6.63 multiplied by 10 to the negative 34, then multiplied by what? The 1.1 times 10 to the what? 15, the frequency that we got there. Now minus 7.73. Let me try to move this a bit. Where's the other one? Like this, right? Yeah, good. So 7.73 multiplied by 10 to the negative 19. Now from there they said to you this is equals to what? Let's see, when we solve this we're bound to get 6.6 times 10 to the negative 19 joule. This is the solution. Now that is basically that, right? So we can answer point C quickly. Now we have the maximum kinetic energy of the, and they say if the intensity of the ultraviolet radiation that is used there is increased, what do we do? Intensity means frequency. So now the maximum kinetic energy in this case, we're going to talk about maximum and the photo electrons that are ejected. So we say for intensity, increasing the intensity of the radiated light has no effect on the kinetic energy of the photoelectrons. As simple as that. There will be no effect, right? So there will be no effect for Roman figure 1. Now for Roman figure 2, there's we're saying what? Increasing in intensity of that will increase the number of photoelectrons. So obviously there will be an increase in number of photoelectrons. You'll excuse me, you'll excuse the laptop, it does misbehave sometimes. Yeah, I think it's misbehaving like that. So yeah, in photoelectrons, that's how we can answer the question. Now that is basically that. Now we have the line spectrum, emission spectrum, and whatnot. So for the line emission spectrum, you're just gonna use the energy levels and whatnot, right? Yeah. Now I'll leave most of the work for you now. Now it's not most of the work, it's just little work there where you'll be dealing with absorption spectrum. We have different types of absorption spectrum, right? So we have the continuous spectrum, the emission spectrum, and the absorption spectrum. Then we have the transition levels there, right? The transition levels, we have level number 1, level number 2, level number 3. So now, yeah, that's basically that. You need to know more on those. Yes. And then the line emission spectrum, right? We can say this spectrum that consists of distinct lines of different colors against a black background. So this is basically around black body. To understand this, go and study black body. You'll get to more information on this. Yeah, for calculations we're done, so we'll continue with theory next time up and we wrap up. Cool.